Hi, I'm EteeKawna Roy and I'm working as a research assistant in Dr. Brandon A. Kemp's Electromagnetics Research Group at Arkansas State University. Today I'm going to present our research on development of multiparticle dynamic simulator for electrostatic self-assembly. So first consider a particle system, microscopic particle system consisting of background fluids and dielectric particles. If the background has larger permittivities compared to the dielectric particles, then the system is called inverted dielectric. So in such systems, researchers have shown that two or three particles may form minimum energy equilibria. For example, consider figure 1 where we can see that three particle systems are forming monopoles, dipoles, and quadrupoles. The electrostatic force among these multipoles is enough to form the minimum energy equilibria in such system, and we will show that in our experiment. So for this, we need to design a simulator that would help us understand the dynamics of the system, that would help us find the minimum energy position of the particles. So for example, consider this diagram over here. We can see there are some larger positive charged particles, some smaller negative charged particles, and all particles are resting on some background fluid, for example, oil, and the particles are initially separated by some distance. So we can also see that light is incident on the system and is being reflected with a different color. That means the reflected light have different frequency or wavelength. This reflected light frequency or wavelength can be varied using the variation in the spacing of the particles. So this spacing variation can be achieved using the external electric field applied to the system. So we can form optical filter with this type of properties where we can tune the optical filter property using the external electric field applied to the system. So to design the simulator, we use this equation where we can see the force component is the main component, and this force can be calculated using either monopole approximation, the dipole approximation, or using the exact analytical solution. So for our system, we use the exact analytical solution and we calculated the force components acting on each particle using the mode coefficient B and W. This is the two particle arrangement for our system, and in figure B we can see the force on top particle versus the separation with various modes. For example, for mode 8 and 10 we can find the stable equilibrium position to be here. Above this point the force is positive and below this point the force is negative. So above this point the force is repulsive in nature and below this point the force is attractive in nature. In between there is a non-touching equilibrium position which is within 0.35 to zero point 0.4 micrometer separation range. So this separation can be varied using the external electric field, and we can see this in diagram C. So for our two particle system, we applied electric field to be from within the range of minus 1000 volt to 1000 volt and find a variation in the equilibrium separation. We ran our simulation and find some movies for visual presentation. So in this movie, we can see how the topmost particle reaches the non-touching separation. This is the two particle system we discussed so far. Initially, the particles were zero point 0.1 micrometer apart from each other, and when they reached the equilibrium, the separation became 0.4 micrometer, which is not shown here. So we are also working with other particle arrangements, and this is the four particle system where we can see the three smaller charged and negatively charged particles are rearranging themselves around a larger positively charged particles, and this is our primary result for four particle system. These are the references. So in summary, we can say that we've developed a dynamic simulator that helps understand the dynamics of the multiple particles and helped find the minimum energy position for two particle system. And we can extend our work either on four particle or more particle. Using this pattern, we can form the larger lattice structure to form the optical filter, and the tunability of the optical filter can be achieved using the application of external electric field. Thank you.